thank you for the introduction, and hi everybody. So Frederick was supposed to present this presentation, but unfortunately he couldn't come, so I had the chance to come and present this work to you today. So I wanted to start with some challenges and motivation, so the kind of challenges that I'm pretty sure most of you guys have encountered when you have been starting to look at this problem. So first, I'm sure we all agree that the geometry of a molecule is something that is rather complex. So just being able to represent numerically a molecular surface is already a pretty big deal. Then if we look at the Poisson-Boltzmann equation, two main challenges arises. So first, the equation is nonlinear, so we need to use the right method for that. And then we talked about it recently, the jump condition at the molecular interface. So we know that the potential is continuous and that the jump in the flux is equal to 0. And we know that there is a jump in the dielectric constant. So how can we impose properly these jump conditions? And another challenge that is very inherent to this problem is the multi-scale nature of this problem. So think about a huge protein. There are definitely different length scale. So you have the length scale of one single atom, and you have the length scale of the full molecule that are quite different. So we need to be able to handle this different length scale. And also, I wanted to point out that there is an extremely fine boundary layer close to the interface in which the electrostatic potential varies exponentially fast. So in this talk, I'm going to start by talking about the molecular surface. I will spend some time, especially on how do we build the molecular surface in this work. Then we'll talk about the electrostatic problem, so the Poisson-Boltzmann equation, and how do we solve it in this work. I'll then show you some numerical result, and conclude. So I'm pretty sure you guys are all familiar with the three surfaces I've presented here. So the van der Waals surface, the solvent accessible surface, and the solvent excluded surface. So here is a small diagram, very simple one for a molecule composed with only two atoms. And so you see the van der Waals surface, which is the reunion of the two spheres. You see the SAS here and the SES here. So in this work, we used the SES surface as the molecular surface. And before I show you how we actually represent and build the SAS in this work, let me talk briefly about the level set method. So this is a numerical method to represent and handle any arbitrary geometry in 2 or 3D or even more dimension. So think about, imagine that you have two domains, omega minus, omega plus, separated by an interface gamma. The idea of the level set method is to define a level set function, phi, and this function is going to be equal to 0 on the interface gamma. It's going to be positive on one side of the interface and negative on the other side. And there are a couple of very interesting properties with this representation. So first, we can easily locate the interface because we have this implicit representation. But also, we have access to geometric quantities such as the normal of the interface just by taking the gradient of the level set function. And if we take the divergence of the normal, we can compute the curvature. So all the geometric quantities are very easy to compute. If the interface is moving, it's actually pretty easy to handle. And one last point that I wanted to mention is that we can reinitialize the function, the level set function, which means that if we have a contour that is represented by a level set function, we can easily make this level set function a nice sign distance function, which has some pretty nice, which can be pretty useful. So let's go back to the SES surface, and especially how do we build it. So we came up with this three-step algorithm. So the first idea is, so given a molecule, so as like a list of atoms with positions and charge, we can easily build the SAS, so at least a level set function representing the SAS, knowing all the position of all the atoms and their radius. Then, so this is the SAS. And so if we reinitialize this resulting level set function, then we're going to have a new level set function that is going to be a signed distance function of the SAS. And now if we think about it, the SES is simply the set of points that is at a given distance, so that is at the radius, at a distance equal to the radius of the solvent or the probe. So at this distance from the SAS. And so if we know the signed distance function for the SAS, we can compute the SES simply by subtracting the radius of the probe to reinitialize the level set function corresponding to the SAS. So this method is pretty straightforward and numerically it's like pretty efficient. The issue that arises when you use this method is that you can create inner cavities. I think Walter was talking about this kind of phenomenon. So here, this is so for this molecule, we use the algorithm I just presented. And in fact, as you can see in green, there are some inner cavities. So if you decide that these cavities have no physical meaning, you need to find a way to remove them. And so I'm pretty sure, I'm sure there are plenty of ways to do so, but one easy way is to realize that all these small cavities inside the molecule are not connected to the outside of the molecule. So imagine that you put your molecule in a big box and you solve this kind of equation. So that's like pretty much just a diffusion equation in the outside of the molecule. So if you solve this equation and you impose, say that, so you are solving for an arbitrary function c, you set it to be on the boundary of the computational domain. So everywhere in this part of the domain, the solution c is going to be equal to something between 0 and b. And at the cavity, in the cavity, since there is nothing diffusing, the solution c is going to be equal to 0. So by solving this simple PDE, you can easily detect if a point is inside a cavity or not. And then if you recognize a cavity, you can simply remove it. So I'm not going to spend too much time on the Poisson-Boltzmann equation, because I'm pretty sure we all know it by now. So the only thing that is specific here, so first we take the nonlinear Poisson-Boltzmann equation. And then, so I use this notation, so kappa squared of x, because so we assume that so we have the molecule with the inside of the molecule and the outside, and so this term, which is due to the salt concentration, is only present outside of the molecule. So by using this notation, we have the freedom to say that this coefficient is equal to 0 inside the molecule and equal to something else outside. Also, so this equation is valid in both inside the molecule and outside. And so the epsilon coefficient here is different in both domains. So this is the nonlinear Poisson-Boltzmann equation. And this equation is completed by these two jump conditions, which are the continuity of the electrostatic potential and its flux. So the way we solve this equation is by decomposing the solution into its singular and regular part. And so for the singular part, we take this expression. So it's pretty standard. And what I want to say here is that at the end of the day, we end up with this equation to solve. So that's pretty much just the Poisson-Boltzmann equation. And now we still have the continuity of the electric potential, but we have a jump in the non-zero jump in the flux of the potential. So let me talk about our Poisson-Boltzmann solver. I just want to start by giving you a quick overview of the method, and then we'll talk about some of these points in more details. So first, our method is implemented on octree grids like Alexander did. This method is a hybrid method using finite differences and finite volume methods. We were able to come up with a sharp implementation for the jump condition, so that the jump conditions are implemented exactly at the interface, considering that there is two different dielectric constants in each domain. We handled the nonlinearity in the Poisson-Boltzmann equation using the Newton method, which is pretty standard for this kind of problem. And for the solver, we use a typical preconditioned BCG stab solver. And so in practice, solving for the electric field on a molecule with millions of grid points take less than 1 hour in serial. So just to give you an idea. So I'm not going to spend too much time on octree grids because I'm pretty sure Alexander spent already a lot of time on that. So the only thing is that I just want to point out that when you build an octree grid, it's pretty simple to. It's actually pretty simple and much faster than building a mesh if you are building a conform mesh when you are using finite elements, and you have a lot of freedom in the way you can refine your grid. So in this work, we decided to refine the mesh close to the molecular interface. And one thing that is actually pretty nice about this work is that our trees are non-graded, meaning that the difference in the size between two adjacent cells can be pretty much anything, because in a lot of work, people use graded octrees, meaning that the aspect ratio between two adjacent cells has to be less than 2. So, for example, these two are graded, but here you have this one is 4 times smaller than this one, so this mesh is non-graded. And so it can appear to be a small difference, but in practice it's very interesting because it gives you much more adaptivity and mesh generation freedom. And also checking that your mesh is graded, or even making a graded mesh, can be pretty highly computationally expensive. So I just wanted to illustrate the grid generation procedure. So if you have a given molecule here for which we build SES, then we build the quadtree grids, refining where the interface is. So I don't know if you can. So yeah, that's the 3D mesh, but we can probably, maybe the 2D cross section are better. And so here I just want to show you once again how adaptive these grids are and how we are able to handle a very different length scale. So this is the bigger cell, and if you look very close to the interface, you have extremely small cell. And once again, for example, here you have the mesh is non-graded. The issue when you use this kind of grid is that if you try to do finite differences, for example, say that we are at this point in the center, you might be missing neighbors in some direction. But there is a way to go around that and define ghost nodes and still get accurate schemes, so second order accurate schemes. I'm not going to explain in too many details how we can approximate, we can do typical classical finite difference methods on this kind of mesh, but I just want to tell you that this is possible and that we can achieve a pretty good, we can achieve a second order accuracy. So that's so when we're far away from the interface, we can just we use these finite difference methods. When we're close to the interface, that's where the problems arise, because we know that close to the interface, we're gonna have the molecule. So by definition, the molecular interface is closed, and so we're gonna have somehow to impose the jump condition on the interface. So if we look at this case, so this gray cell is crossed by the interface. So one part of the cell is in one part of the domain, and this part of the cell is on the other side. And so here we use a finite volume approach, and so you have to think that this cell has in fact two values. So one value for the solution in this part of the cell, and one for the solution in this part. And so if you want to do a finite volume method, one way to do so is to write the finite volume approximation for each of these two values. So the value inside inside this domain and inside this domain. So here we decided to do so only for, I mean, since the two equations are pretty similar, I just wrote them for one. So here we're writing the equation for phi plus. So the solution of the Poisson-Boltzmann equation in this domain. And so this is the resulting finite volume equation. And as you can see, this is just a sum of all the flux on all the sides of this domain. And approximating this flux on the side of the cells are pretty easy. You can just use this formula that is pretty standard. The issue is to approximate the flux on this part, on the interface. And to do so, we're going to be using the jump condition. So this is the jump condition in the general case. So just the jump between the two flux is equal to some given function. So the problem is that here we want to know the flux, and here we have the jump in the flux. So we need to find a way to approximate the flux from the knowledge of the jump of the flux. And so the way we did it is by, so first we have this expression, and then we express this difference using the value of the solution inside and outside the interface at the different grid points. And so now if you look at these two equations, you have two equations and two unknowns. And so you can solve these two equations, and you get two expressions for this quantity and this quantity that you needed for here. And so now we can approximate the full finite volume equation. So the nice thing about this method is that first it's sharp in the sense that the boundary condition, the jump condition, is imposed exactly at the interface. We don't have to assume that the dielectric constant is varying smoothly from one domain to another. So there is really a jump in this coefficient. And also it is, so if you look at this expression, I don't know if it's clear, but you can see that it's rather simple, and it's only making use of neighboring points. So that means that the structure of the matrix is going to be changed, but not that much, which is always a nice thing. So let me show you some numerical results. So first, I wanna start with this very simple case. So imagine that you have this molecule composed of 3 atoms. And so this is the probe, and so we build the SES, and then we use our Poisson-Boltzmann solver for this geometry. And sorry, we just compute the surface, and we compare so the surface position and area with the one given by the MS software. And so here are the results. So both the position of the SES and its surface seems to be pretty accurate. Then, so we did pretty much the same thing, but now considering real proteins with different numbers of atoms. And so we compared the surface area given by the MS software and the one that we got in using our algorithm. And so if you look at these three columns, they give a pretty close results. So we're pretty happy about that. So now that it seems that the SES surface is properly constructed, let's look at our Poisson-Boltzmann solver. So here is an example where we took this molecule and we built an analytical solution, as you were suggesting before. So this is the analytical solution, and we just did an accuracy analysis. So we start on a given octree grid, and then we recursively split every cell and compute the error. And from this example, it seems that the method is second order in L1 and L2 norms, but only first order in L infinity norm. So here is another example, which is probably more physically meaningful. So we took the Kirkwood solution. So this one is not exactly the nonlinear Poisson-Boltzmann equation, because you have this molecule with a charge in the middle, and then you have this layer in which there is no salt. And so you have just the Poisson equation, and outside you consider that you take for the Poisson-Boltzmann equation the linear version, so you end up with this equation. And so it's not exactly the equation that we build our algorithm for, but it's pretty close. And so we're able to solve this problem and compare our results with the analytical expression. And so once again, we can see that the L1 and L2 errors are roughly second order, but the L infinity norm might be a little bit, the accuracy in L infinity norm might be a little bit less than the one in the L1 and L2 norms. And so another thing that I wanted to say about this example is, so this is the error analysis in the whole domain. So we compute the error in the whole domain, and yeah. And so here, this is the error analysis, just taking in account so the blue section, so close to the two interface. And as you can see, the error is pretty much always the same, meaning that the error in this kind of problem is arising at the interface, and that therefore refining close to the interface and using the kind of grids that we have been using is a pretty good idea, because the error is there, and so that's there that you want to put some effort. One last test that we did was to so we computed the solvation-free energy. So here is the formula, and here are the parameters that we used. And so we computed this energy after we computed the electrostatic potential, and then we compare our result with the one given by APBS. And so we took this set of molecules, and so that's the relative difference that we got. So the biggest one being 1%. So it's pretty good, and we're pretty happy with that. I just wanted to end this talk with an illustration of the capabilities of our software and of the octree framework. So here we took a DNA strain for the molecule, and we looked at what happened when we refined the mesh. So we start on a small grid, and then we recursively split the cells that are close to the interface. And so here we have like very few grid points, and as you can see, the SES surface is not very refined, and we cannot capture the smaller details. And as we refine the grid, the surface is getting more and more accurate, and even so the potential that is depicted on the surface get more and more accurate. And if you keep increasing the resolution, then you see that it's getting harder to see the difference in the surface and in the electric potential. But so I just wanted to point out that this kind of resolution on an octree, that's feasible. So that's so the max resolution is 1024. So meaning that you have at most you have 2 to the power 10 grid point in one direction. And so if you were to try to do that using uniform mesh, that would be just impossible, or take just like, so if you do the calculation, I think you would have like 200 times more grid points. So maybe you could do it, but yeah, you would need a very big machine and you couldn't go very, I mean, that would be the maximum you could do. And so, yeah, once again, by using this kind of framework, we're really able to handle big molecules with a lot of atoms, and I'm pretty sure that we can go further, considering bigger molecules or more molecules with very fine grids. And so, to conclude, so we developed a framework for the Poisson-Boltzmann equation and an application to the biomolecular computation, so in which we developed so first the Poisson-Boltzmann solver, and we show that this solver is make use of a highly adaptive data structure, which is quite interesting. We show that our results were accurate and agree with other software prediction, but also we developed a way to build the surface of interest, which in this case was the SES. And now the two next steps that our future work, I think we want to try to couple our Poisson-Boltzmann solver with other solver. So for example, that would be interesting to be able to model the surrounding fluid and maybe study the coupling between the fluid flow outside of the molecule and the molecule. So think about maybe microfluidic application. And another point on which we actually started to work is the parallel efficiency. So because the calculation can take quite some time, and if we want to look at even bigger cases, we're going to have to have a very efficient algorithm. And so right now we are working we're trying to use the PETC and PForest library to have a good parallel speedup. And so I would like to thanks my colleagues, so Frederic, Mohamed, Azdis, and David, and also our sponsors, so the Department of Energy, the National Science Foundation, and the Office of Naval Research. And thank you for your attention.